I hope you're enjoying Astronomy 10 so far. This week we are getting into week 2, and there's a lot of stuff, especially with the third hours, having to do with sky and star charts and things like that. So we're going to walk through a few of those. We have here our origins and maps describing positions. You want to represent positions with coordinates, and you're probably familiar with this a little bit. If you have flat surfaces, there are 2 dimensions. There's a coordinate system in this room, for example, although technically it's a 3-dimensional room. You can even have a coordinate system for Rockland. So let's, and even on a sphere, you can have 2 dimensions. What we're going to see here is we have different coordinate systems for the Earth and the sky, although as we're going to see, they are related. So here, for example, here's a picture of Sierra College. Now, if we were doing this and we were trying to develop a coordinate system, you would have to have an up and down coordinate that a lot of people will call Y, and you have an left and right that a lot of people will call X. Now, one of the things you also need is an origin, and maybe you would set the origin to be here in the lower left corner where my image disappears, and that would be 0, 0. But the place is, you need an origin. Now, that works for a flat map, but as I have here, you see the Earth, it is 3-dimensional and it's a sphere, but since we're just working on the surface of it here, 2 dimensions works. And this is the coordinate system that we have used for a long time, latitude and longitude. And even as it's spinning, we have a set point. Say we're over here in California, we have a set position called longitude and latitude that I'm assuming most of you are familiar with. Now, we need origins with this, and the first one, latitude, there's some nice natural origins, which are the poles where it appears to rotate around, and the point halfway in between, which is the equator. And this is set up nicely so that if you're on the equator, you're at a 0 degrees latitude, all the way up to 90 degrees north, or way down here, down under, about 50 degrees south, but all the way to the bottom, 90 degrees south. Now, the longitude are the lines that run this way, okay? And they run through the pole, through the equator, down to the other pole, kind of like this. And those needed a starting point also. And I'll tell you the truth, it's a little bit more arbitrary. It runs through England, specifically the, get England over here, the Greenwich Royal Observatory. And to be honest, it's partially that because the English set it up that way. They had some logic to it, and that is the other side is where the day starts. That's the international date line. I don't know if you can see it there. It's kind of red. But anyway, so that's on the other side. And the other thing they do with longitude that's interesting is they run it west one way, like to where we are, and east the other way. Okay, so those are our longitude and latitude systems that we use there. System, but it's even though we are looking up into the sky, it's almost as if we were looking inside of a dome. Okay, and this actually we need to be able to find things, and like I'm going to make a kind of a big star over here. Probably easier to see if I do it on the white. Okay, and I need to know where that position is. Okay. So again, we're kind of a review. We have our longitude and latitude here, and everything you need a reference. Again, for the terrestrials, like North Pole, equator, latitude, and longitude, and the prime meridian. That's the 0 point. That was the one I was talking about that they started in England. Oh, so sorry, I wasn't quite done here. So what we see is there's the equator, there's the 0 degrees, 10, kind of 15, 30. 45, 60, all the way up to 90 down the south, and the prime meridian runs through England, and then it runs east one way and west the other. Okay. Now, of course, we have our position on that. I showed Sierra College, but it has a very specific position, and that is 39 degrees north longitude, 121 degrees west latitude. 39 north latitude, west longitude. One thing to point is degree is actually pretty big, so a lot of times they'll go down to decimal degrees. And if you're doing a GPS to find somewhere in a car, it's very, very detailed where it is. Okay, so now going to our little fake star here. If we needed to find something here, we needed some points of reference. So there are some things they wanted to attach to this and go from here. It is the height above the ground. So anything directly on the horizon has an altitude of 0. Anything directly overhead, if we were to point straight up, is called the zenith. And that has an altitude of positive 90. And of course, anything in between is some other value. Notice Polaris over here is at 40 degrees. Altitude, we'll come back to that. That's really important. But some other star at this certain time of day, its altitude is right there at 30 degrees. Okay. Now, the other part is called azimuth. And that is another thing that is a lot of times called direction. And they started at north, so facing due north is 0 degrees, east is 90, south is 180, west is 270. So if you want to give the position of an object, for example, the star in the Big Dipper has an altitude of 330 degrees, altitude of 30 degrees and an azimuth of 330. 2 locations point there. Now, another thing that's important is there's an imaginary line that runs from north through the zenith to south called the meridian. And that's important because if something is rising in the east, it is rising until it hits the meridian, and then it is now, if it's west of the meridian, it is setting. Okay, so if you're rising, you're east of the meridian. If you're setting, you're west of it. Also, when you're on the meridian, that is your highest altitude for the day. We will talk about there are some stars that cross the meridian twice. That's something called circumpolar, and we'll get to that. Okay, so now, again, we have altitude and azimuth, and those move along pretty good. Now, there is one problem with this, okay, and that is it is a function of position and time. Meaning, if it is a certain time of day, and I'm sitting here in California on my globe like this, and I'm pointing to some star off in distant space, it will appear to be there. But as the day rotates and the star rotates, it will change where it is pointing. Maybe I can kind of do this. Meaning, if I'm looking at a star somewhere over here, I can't get it. Sorry. At a certain time of day, as it rotates, it will move. Now, the other problem with this is the fact that, let's say I'm here, and my friend Harry down in Australia is there. We're pretty close to it. I apologize. He's out on a ship in the ocean. And the point is, I'm trying to get it in here, is that we're pointing at different parts of the sky. So the key fact I'm trying to get across here is that this does not work on a permanent designation. If you were giving altitude and azimuth of objects, you would have to premise it with your 1, location, and 2, time of day, which is pretty rough. Okay, so please note this is not fully covered in the text, so I want to go over this. This brings up what's called the equatorial coordinate system. And this idea comes from the ancient Greeks. When they came up with the idea of what they called the celestial sphere, they literally believed the Earth was in the center, and there was a giant, honestly, crystal sphere where all the stars in the Milky Way and everything out there moved on. Everything else, planets, the sun, the moon, were between us and that. Now, that is not correct, obviously, but it's a pretty good representation of what happens. So as this appears to rotate around us, we can see the objects moving with us. Now, what this has done is, again, the celestial sphere is the sphere of heavenly objects that seem to center on the observer. And we have our points of reference, just like we did on the Earth. You have the North Celestial Pole, or NCP, the South Celestial Pole, and again, an equator, which is called the celestial equator. So we have some reference points already that we can maybe develop another coordinate system. In the north or southern hemisphere, one can see the north or south pole directly above their north or south geographic pole. We are lucky in the northern hemisphere. We have a star that is almost exactly on this, and this is called Polaris. Southern hemisphere, they don't get a star like that, unfortunately. It's luck, really. Now, just like longitude and latitude, there are lines that measure position here. The first one, which is similar to latitude, starts at the equator at 0, goes to positive 90 at the North Celestial Pole, a negative 90 at the south celestial pole, and that is the one here called declination. So it is set up exactly like latitude, but it uses positive and negative instead of north and south. Now, the next one, which is called right ascension, is similar to longitude but different in three ways. One's a little bit different, not a big deal, in that the 0 point was a little more democratic. It is this point here called the vernal equinox, where the ecliptic, which is the apparent path of the sun, crosses the equator. So that's always a fixed point in space. You'll see it on, it's right in the middle of your SC001 star charts. So that is the ecliptic. So there's the 0 point. The other two differences are, one, it doesn't go east and west, it goes all the way around. So it starts at 0 and comes back and starts over. And the other part of that is it's not in degrees, it's in what are called hours, minutes, and seconds. And the reason why they do that, it is tied to the rotation of the stars around the night sky, and something called sidereal time, which we may come across later. So that's why they use it. So it's, instead of giving it in degrees, it's given in hours, minutes, and seconds. And just kind of a mental thing to catch it with is 1 hour is about 15 degrees in the night sky through normal circumstances. You may be wondering to yourself, why do they do this? Do they come up with this coordinate system that is off like this? And we're going to see it's not aligned exactly with the horizon like it was. And the key is these coordinates are glued to the sky. As you notice, as the sky moves here, the Earth stays still. So if I see this star right here at a certain point in time, it has a set coordinate. And it doesn't matter if it moves over here and then Harry in Australia or a different time, that coordinate is set. And that is the key. It is an extension of the terrestrial longitude and latitude, but it's a huge tool because it's fixed in time. Now, this is a kind of a diagram to explain this. So here's a star. Here is the celestial equator. Notice it's this green line at 0 degrees declination. First thing we do is measure up to its declination. So this would be, let's say, 20, 35, I don't even know what these are. So let's say it's 20, 40, 60, 80, 90, I don't know what these are. So let's just say it's about 70 degrees declination. Now, here's our 0 hour of right ascension. Notice it's where the equator and the ecliptic, again, this is the sun's path. Notice it's pointing to the vernal equinox. So then when we measure over, my guess are these are in hours, 1, 2, 3, 4, about 5 hours. So the location of that star would be 5 hours right ascension, 70 degrees declination. And that's how you would find it. And it never changes. Basically any point in between, and we'll see this in a second, the equator and the pole. So this would be like an average location. So what we see is the star is going to rise in the east, go up to its maximum altitude, and then it would set in the west once it crosses the meridian. Again, we talked about the meridian. Now, at any point in time, you could go and measure the altitude and the azimuth. Remember, 0, 90, 180, 270, that's the locations of the azimuth. Or you can measure, if you knew its position above the equator, this one's on the equator, so this one would be different, and its position away from the vernal equinox, you can measure its exact coordinate that way. Now, what I want to show here is, again, what happens when you have the differences. So if you were on the pole, the point directly overhead, again, would be the zenith, and that would match up with Polaris at 90 degrees declination. And all the stars would appear to circle around that. Okay, so one of the things that you're going to note there is the altitude of those objects doesn't change, but the azimuth does. Now, if we flip down and we are now on the equator, the interesting thing to point is, even though now that the Polaris is at altitude 0 on the equator, its declination is still the same. Remember, the right ascension and declination do not change. And now everything would appear to rise and set, meaning their altitudes would change over time, but their azimuths would be about the same. Okay, an intermediate position is really what is happening most of the time. So the pole is at a certain altitude at declination 90, and it's just going to move kind of around that other point. Now, one thing to notice, at this point, altitude was 90. Okay, that's that's our latitude. Here we're at latitude 0, altitude of the pole 0, and let's say we're estimating this, we're at some latitude 45 degrees, pole's about 45. So one of the key things, you may have seen it, is altitude of the celestial pole is equal to the observer's latitude, and that is key. For example, in Rockland we're at about 39 or 40 degrees. That means that Polaris is at about 39 or 40 degrees altitude. If we were in New Orleans, that has an altitude of 30 degrees, the altitude of the North Celestial Pole would be 30 degrees. Now, because of this, we have some other things called diurnal motion or daily motion. Stars are fixed on the celestial sphere. Remember, they're kind of fixed on this as it spins around, which rotates from east to west on a minute-by-minute basis, completing one full turn each side of the old day. This is called diurnal motion. So one of the things we should note is that there are regions in the northern hemisphere where some stars never set. This is called the North Circumpolar region. And then there are regions in the southern hemisphere where some stars never set. Now, remember, we are at 40 degrees, roughly, latitude, and thus Polaris is at 40. So anything from 40 down to the horizon can be seen. Okay? So anything... this is relating to the declination. Remember, the declination is 90 degrees. So anything around that goes can be seen. So the point I'm trying to make is there's a connection between your latitude and what declination you can see. And realize, if we go back, to this, and we see that if this was an altitude of 40 degrees, anything from here to the ground, so a difference of 40 degrees, can be seen. So, but if this is a declination of 90, that means anything of declination down to 50 degrees would be circumpolar at our latitude. So basically the thing is, it's 90 minus your latitude, and anything above that is circumpolar. I'm not sure if you've seen one of these, but basically this is also a representation of what's going on, meaning that as the night sky appears to rotate, it does around this, actually this point right here, but that star really right there is Polaris. So this is quite a few hours as the sky rotates around it. So again, the key point here is, as the day appears to rotate, the stars will appear to rotate around that fixed point in the sky. In the north it's Polaris, in the south it would be the South Celestial Pole. And their declinations and their right ascension stays the same, but as they rotate around the day, some will be circumpolar. For example, all of these objects here are circumpolar, down to about right here. You can't really see it because the trees there in the image, but this is going to be that declination minus whatever this altitude is, which again is equal to your latitude. South, you just don't have the central bright spot. So again, for example, this star is going to be circumpolar, barely, because its declination is 90 degrees minus whatever this angle is. For Rockland, that would be 40 degrees. For New Orleans, it would be 30 degrees. So again, what we would see here is for northern observer details. For objects in the east, the stars rise, the altitude increases, the azimuth increases. For the south, the stars rise and set, altitude increases and decreases, azimuth decreases. In the west, this is where stars set, altitude decrease and azimuth increase. In the north, stars neither rise nor set, but rotate around the pole. There is circumpolar motion, and you have altitude and azimuth both alternating, increasing, decreasing. So they will go up and go down as they go around. Okay. In the east, they're going to rise, altitude increases, azimuth increases. Again, south, you're going to see kind of arcs where they go up and over, rise and set. Again, west, you're going to see them altitude decrease, azimuth increases, and they set. Now, sorry, I'm going to line these up. Oops, excuse me. So consider a star on the eastern point of horizon. Okay. For the equator, this would it would straight up, it would rise straight up, come over and set. Azimuth would be unchanged. In the North Pole, flip to the other extreme, it would have horizontal motion. Altitude is unchanged and it spins around. This was the diagram I had a few seconds ago. And then For an intermediate angle, both altitude and azimuth increase. All right, so next thing we have are constellations. Constellations, from Latin meaning stars together, is an area of the sky containing a pattern of stars named for a particular object, animal, or person. Earliest constellations were defined by the Sumerians as early as 2000 BC. Today they have been formalized by the International Astronomical Union, IAU. And the 88 constellations we use today were established by agreement. Things that are not constellations are things like the Big Dipper, Little Dipper, Orion's Belt. Those are called asterisms, or an unofficial arrangement of stars. Well, that's it. I am going to go over some more on star charts and angles in future lectures and videos. But again, please review this, and if you have any questions about the coordinate systems, just send me an email at any time.